Welcome to Lab 2, Motion of a Falling Object. The purpose of this lab was to observe the motion of an object dropped from rest and construct a model based on Newton's second law to compare the data. In conclusion, it was found that as the paper ball fell, it was accelerating downward due to the force of gravity. A drag force was present in the opposite direction that also affected the paper ball's fall. For this video, I videoed a paper ball dropped from rest. The video shows the points at which the ball was tracked. The table on the right shows the position versus time data as the ball falls, and the graph shows the y position versus time of the ball's motion. The data found in Tracker was then used to construct a model using VPython, but before the model can be constructed, I had to figure out what forces were acting on the ball. Newton's second law states that the final velocity equals the initial velocity plus the net force divided by the mass of the object times the change in time. The initial velocity of the paper ball was 0 in this case. The net force can be found by adding all of the forces acting on the paper ball. The free body diagram shows that gravity is acting in the downward direction and drag force is acting in the opposite direction. Adding these forces together gives the total net force. I added in my data and information into the code to create the model. I added the ball's mass and the initial position and initial velocity vectors. For the drag force, constant b, I had to guess and check different values to get as close to the ending position as possible. I added in the equations for weight and drag force and added them to get the total net force, along with the equations for predicting the ball's velocity and predicting the ball's position. When I hit Run Module, a model of the paper ball falling comes up on the left, and a graph of the position versus time comes up on the right. I created a graph of experimental versus model data using model data that has a drag force of 0 and data that includes drag force. All three graphs are very similar and only differ towards the end. The model that accounts for drag accurately predicts the final position and is very close to the experimental graph from about 0.2 to 0.5 seconds. The graph that does not account for drag overpredicts the position of the ball because the only force that it involves is the force of gravity. The model that accounts for drag includes gravity and drag, so it gives a better prediction of the actual paper ball falling. Error occurred in the center area of the graph due to human error because I may not have accurately tracked the center of the ball for each frame. The model with drag and the model without drag both show the acceleration of the ball in the negative direction. The slope of the position versus time graph is velocity, and the velocity is increasing as the time goes on, meaning the ball is accelerating. Neither of these graphs predict the terminal velocity because the terminal velocity is reached when the downward force of gravity equals the upward force from air resistance and the object stops accelerating. Both of these graphs show that the paper ball is still accelerating at the end at 0.6 seconds. The graph that does not account for drag does not account for a force to equal the gravity in the opposite direction, so terminal velocity is not reached. The graph that does account for drag does not reach terminal velocity either because the velocity is still increasing at the end. But if the model ran for longer, terminal velocity would be reached after a longer time period. If the paper ball was initially thrown downward, it would reach the same terminal velocity because the terminal velocity is based on the object itself, not its initial velocity. Just like the terminal velocity isn't reached in the time interval shown, a thrown ball will also not reach its terminal velocity in the time interval shown. Theoretically, however, the drop ball and thrown ball would reach the same terminal velocity.